based in Vancouver, Canada. We have been a company since 2014. We have pivoted to do this, conversational assistants, about 2.5 years ago. We're now venture-backed with investment from Flying Fish from here in Seattle, Yaletown Partners in Vancouver, 1843 Capital in New York, and BDC Capital in Toronto. So we have about a team of 55 people now. Around 30 or so are engineers or data scientists. And our product looks a little bit like what you can see on the right-hand side. So essentially we provide the ability to ask questions to your bank, be it being able to digitally self-serve yourself, ask questions about technical issues you're having with your bank account, as well as provide transactional capabilities within your banking services. So for example, you might be asking what your balance is or what you're spending money on using natural language, using a text interface. Our public deployments are around the world. Some of you might know BMO, which is a Canadian bank. Time Digital, which is based in South Africa. Fedor Bank, which is German. So we have German, French, Spanish, and English offerings in production right now. HB Financial is another Canadian bank, which was the first to offer fully featured transactional banking using Facebook Messenger through our service. And then Banpro, which is a Latin American bank, which is based in Nicaragua. We also have partnerships with Visa, Visa Canada, Temenos, Capgemini, Auth0, amongst others. And I think I'll just pass on to Kavan now. So Kavan is a data scientist on our team. He's been with the company almost 2 years. And he's been instrumental in developing our technology, proprietary technology. And then he's going to share a bit about what that is, how it works, and what we're doing with it.
Thank you for the introduction, Ken. As you mentioned, Kavan, I'm a data scientist at FinAI, and basically today I'm going to talk about intent classification with how you can build intent classification models with MXNet, and basically some overview of how natural language understanding works, along with an overview of dialogue systems. And some variants of some explanation about neural dialogue systems as well. So to begin with, this basically is a type of text classification. And for those of you who are not aware of this, text classification it's basically a technique where you could have some amount of text data, and you classify those into several different categories. As you can see here, we have a group of documents, and they are all classified into 3 different categories, which is technology, sports, and entertainment. This basically involves a bit of human annotations to classify these documents into those predefined categories, which are also human defined. You could think of text classification where an annotation is done at every single text. The text could be at a document level, or so you could be classifying a document itself, or you could be classifying sentences of those documents, or you could be classifying phrases. So there are different levels at which these text classification models can operate. So that's what I'll go over. And in terms of applications of how these text classification models are used, you could think of basically whenever you are able to annotate to some type of data, in terms of whenever text is concerned, if an annotator can do that, it's likely that a machine learning model can also do that. If you are able to identify several different categories and classify them in those, some applications that you would have seen in real world is detecting spam email in your inbox, where it's filtering it out in spam box, and the important ones would be delivered straight into your inbox. The other one would be detecting abusive comments online on different social media platforms, where you can filter them out, or just tracking sentiment, customer sentiment over time. And the idea basically here is mimicking the annotator. If annotator can classify that, model should be mimicking that and classify the same categories. And today we are going to talk about how these text classification models can be built. And the main idea about this is when you build such type of classification models, the techniques we are going to discuss is not something that you can only use in text classification models. Those techniques can also be used whenever you're dealing with any kind of text data, and you can think of different applications where you can apply these model techniques. So think of these as, in this case, it is classifying in different categories. Let's say if you're building a recommender system, in that case, your features could also include text data. So if you're classifying or recommending a user product and it includes some title description of that product itself in text data, you could leverage that text data and apply these techniques and convert those into features, and that can also be used in recommender system. And the same thing is if you're trying to frame that in a regression problem. A problem could be if you're trying to take the data, looking at the blog post, if you're trying to predict how many viewers will hit this blog post, you can actually frame that in a regression problem by looking at the similar techniques in the initial phase of your model, and then you can, I'm going to explain what the last phase looks like, but you can actually frame that in a regression problem where you can actually predict how many views an article would get. So this is an intent classification. It is a text classification problem in terms of any conversational assistance or conversational AI is concerned, or think of it as any dialogue system where there is an interface between a user and a system. And this is basically framed based on what the user is intending to do. So that's the first step we capture. And you could basically think as there is some user input that comes in from the user. In this case, the user utterance is basically what's the balance of my checking account. In this case, we have two different terminologies here. First of them is intent recognition and entity recognition. So these are two different machine learning models. We're going to talk more about the intent recognition model, but how this utterance can be mapped to a response from the system is basically the first machine learning model would try to predict what category of the intent does this utterance belong to. So in this case, what's the balance of my checking account? You would see the intent category is get balance. That's what is being predicted by the intent model. So that's the first step of classifying the main intention of the utterance. And then we have something called entities, which is kind of a tagging model. The main purpose of entities is to find out the key information pieces out of these utterances. So you know the main intention of the utterance, but you need to break that down into which type of specific details that utterance is trying to provide. So in that case, in this particular scenario, we have what is my checking account as an entity. So our entity recognition model is going to tag the checking account as an account name, and then we concatenate these two outputs from the machine learning models, and we provide some response based on some business logic attached to these different combinations. So before I'm going to show you the sample of how these models can be built using MXNet, I'll just provide some more description of how we've used such kind of models in the past, and what basically this overview of model looks like when it comes to text data and how these neural networks would work in this scenario. So think of it as you have a sentence coming in this particular scenario. I like this movie very much. The main idea behind this is we first of all we break this sentence down into tokens. So it would be 7 different tokens in this scenario, and then we convert those tokens into some form of numerical representation, which is basically just a lookup table which will basically map these different types of text tokens into some type of numerical representation. In that case, we often use word embeddings, which is basically a higher dimensional mathematical representation of different words, and these models are built based on what's the context. So think of it as word embedding models that are built such that we feed a word embedding algorithm a large corpus of data, and it's going to go through each of those words. And the main idea of that algorithm is learning where these different types of words occur, how frequently do they occur, and what are the contexts of those occurrences. So in that case, a good and bad might occur together in some of the contexts, and in some of the other contexts it may appear quite different. And the main thing is, if you break that down word embedding, the actual scenario is if you'll be able to find similarities between those type of words quite easily if you're following some nearest neighbor search and trying to differentiate those mathematical representations. So the next layer is basically, we first take these representations first and then combine them all together, and we feed them in different convolutional filters. These convolution filters are basically convolving through the input provided in terms of word embeddings. And then we have different feature maps, which is basically just, it depends on the height of the filter that you have. In that case, it's corresponding to the height, so we have 4, 5, and 6 sizes. And then we take those feature maps, which is a sampled down version of how those convolutional learnings look like, and then we feed that to some kind of activation function, which basically provides some non-linearities. And then we have a max pooling layer, which essentially maps it down into a smaller version of that, which represents that filter outputs. Once we have those max pooling layers, we especially concatenate those together and see how different classes look like. And then at the end, once we have an overview of what different classes look like in terms of where that utterance belongs to, we break that down again into final representations. So in this case, it is a sentiment analysis model, so it is trying to predict positive or negative output of this. So if this is, I like this movie very much, that becomes a positive output. So in that final layer, we basically provide some probability distribution for those two classes, and we pick the maximum probability distributed class. So I'm going to show you how you can build these types of models using MXNet. So, am I audible enough? Yeah. So let's look at these the similar type of model that we saw. It is one of the pretty standard convolutional neural network for text classification problem. And then what we do here is we're trying to build similar type of models, but with some enhancements that MXNet also supports. So I'm going to explain those enhancements a bit further. First of all, we basically load these packages in terms of MXNet and CloneNLP, which is also a library built on the MXNet framework supporting the NLP pipelines. So you have pretty handy functions available in those CloneNLP library. So we're going to look at a state-of-the-art benchmark data set called AG News dataset. In this case, we have a data set consisting of 120,000 training data utterances, or the news descriptions, and in testing data we have about 7,600 records. Basically, we have in terms of features, we have a title of the news article and the description, and we have several different annotated classes. So we have 4 different categories, which is business, sci-tech, scope, and word. So we first start off with loading the training and testing data. We have these in forms of CSV, so we just use pandas to load them. And then
we are just looking at what that data looks like. As I explained, we need a tokenizer to split that tokens and break those sentences into some specific words. So this is where we define tokenizer, where Gluon NLP has a simple interface to Spacey, which is basically an NLP library which provides different NLP tasks in pretty handy functions where you can use dependency parsing, pause tagging, or tokenizing with just simple calls. And in this case, Gluon NLP provides an interface where you can just, with one line of code, you can get the interface to Spacey tokenizer. What in the first step, what we do is basically initialize this tokenizer, and then we start building a vocabulary, which is along with pre-trained embeddings. So building a vocabulary means looking at the entire set of 120,000 records and going through each of those records and trying to find distinct tokens out of it. And then we build that along with the frequencies of those tokens, and we provide some mapping. So every token will have some unique integer representation. And then in order to transform those in some type of mathematical representation, what we can do is we can either use pre-trained embeddings, or we can try to decide to learn those embeddings by ourselves on just our own data. In this specific case, we have provided the option of pre-trained TSML. Pre-trained could be coming from a different library called FastX, or the pioneers word-to-word algorithms, and they are pretty easily available on the web, and you can choose to initialize those with the pre-trained embeddings so that you don't have to learn on your data, and it can learn basically better context of these different words. In our case, in this example, we have disabled that, but essentially if you go through this notebook, if you enable that, you can just run those through pre-trained embeddings. So Gluon NLP again has a pretty good interface with any types of pre-trained embeddings. In this case, we're using the FastX pre-trained embedding. You can also use something called like Glove or word-to-word, and within just 3 lines of code, it builds a complete vocabulary with token to index and label to index representations. And in this case, we just print out what those representations look like. So if you have, let's say, 100,000 distinct tokens in your data set, it will build 100,000 length of dictionary with each unique integer assigned to it. And then we also do that same for the classes that we are going to predict. So we have 4 different classes, so we build a dictionary which is basically mapping classes to the integer representation. And then we start off with some pre-processing method, which is kind of required. The most basic type of pre-processing would be to break that utterance down with a tokenizer, where you can. But in this case, we are using some pre-processing based on provided from the original author of the paper. So it's basically taking out some punctuations, and it just provides better view of 2 different occurrences of similar word, which are distinct by the punctuations or some other quotations or different types of characters. And then we are basically building our data set with concatenating, so looking at every single utterance, breaking that down into different words, pre-processing it, and then transforming a data set through that. And we have something called an array data set, which is an efficient way to load these types of iterables in an MXNet efficient way. And that just provides an iterable to go through different types of mathematical representations. Because since we are transforming the data set, it includes converting these different words to several mathematical representations. So if you look at these data sets, now it doesn't look like text data, it looks all in numbers. And basically once we have that, we are basically defining the sampler, which gives you an idea of how these mini batches are formed. So when you're feeding or training these neural networks or any types of machine learning models, you basically feed your data in some form of mini batches, where you break that down into some batches and then you feed that specific batch in one iteration, and look at how that model learns from that particular batch. So in this case, we're using a bucketing strategy, which is basically an enhancement, which I'm going to explain more about it in the next slide, but it is basically the most naive approach to use in creating these models. Is these models require a specific length of input. So if you're talking about feeding in utterances, you may have a description which is of 2 words, and you may also have a description which is of, let's say, 200 words. So, but model can only take a fixed size of tokens or text in one single mini batch. So what we do here is, instead of going with the padding approach, we use bucketing, which basically groups similar sizes of your records in one batch, and then that batch is specifically fed in the network. So we are just using exponential width bucket scheme, which is basically just defining buckets based on how many token sizes that you have. So we don't discard any information. With padding approach, you might have to discard something, or you just take the highest or maximum amount of sentences and then you pad every other utterances. So in that case, think about the scenario where you would have 200 words, and if you decide to have 200 fixed size, in that case, if you have a separate record which is just of 2 words, you would have 198 paddings in that to make up for the total size. So we're just basically loading in a data loader, which is again an efficient way to sample with this bucketing scheme and then feed that to the mini batches. So if you look at these, this provides how these buckets are formed, and you break it down into different batch sizes. So there are 10 buckets defined here. So this bucketing or data loader will try to frame 10 buckets, which is equally distributed through different sizes of your data. And then we begin with the building the network architecture. In this scenario, as I explained in the previous slide, the model is basically taking in the text classifier as a CNN. So we first start off with initializing an embedding layer, which just takes in what is the vocabulary size. In this case, let's say we have 80,000 distinct tokens in our data set. So the vocab size would look like 80,000, and the output dimensions. So the dimensionality of your word vectors. In this case, we've defined it. It could vary from, let's say, 100 to 300, with 300 capturing more information about it. And that basically initializes the embedding layer, and then we stack multiple convolution layers based on how many filters we define. So in this case, we are using 3 different filters, which is of size 3, 4, and 5. So we're just going to stack 3 different convolutional layers along with the max pooling layer. So it has an implicit activation function of rectified linear unit. And then once you stack these 3 different convolutional layers, you need something which does the fully connected pass. So that's where we define dense. Before that, we also do some regularization, which is using a dropout regularization technique. So this is what basically the network architecture looks like, and this is really useful when you are using Gluon or MXNet in terms of printing out the network architecture, and you could see how many different filter sizes you have defined for different convolutional layers, and basically just look at how your data is going to flow through this specific architecture. And then we start training the model. So we begin with defining a context. A context is basically providing the target device of where you want to run this algorithm. It could be a CPU or it could be a GPU. So I'm just going to run that. I've run that on my machine, so I've initialized it as CPU. And then we do some initialization of this network. So there are different initialization techniques. It could be uniform initialization, or in this case, I've used Xavier initialization, which is just basically a distribution of how these weights are initialized in the first pass itself before we even do anything with the model. And then we have an accuracy evaluation function, which once you start training this model, you will have an evaluation criteria at the end, which tells you, based on the learnings you've done in one iteration, what's the accuracy of your model. And then based on that accuracy, you just try to repeat those iterations until the point where your model becomes really good. So we start off with pre-trained. So this is a flag which is indicating if we are using pre-trained, we can choose to disable the learnings on the embeddings. In this case, we are using embeddings on your training data itself. So we are choosing to learn the weights on our embedding here because we are not using pre-trained. But if you are using pre-trained embeddings, the idea is basically you can also choose to freeze the pre-trained embedding. So whatever you learned from the bigger corpus, you can freeze those learnings and then see how that model performs based on the learnings you had on a much bigger data set. And then you can also choose to fine-tune the pre-trained ones. So that gives, again, some additional benefits based on the data set that you are trying to work with. So it again varies with the data set. So basically we are running through 3 iterations, and it's just running through the data, loading these mini batches that we've formed with the bucketing strategy, and then we evaluate. And if you can see, there are three epochs, so just 3 iterations, we are achieving almost 87% accuracy with this type of model. So this just shows you how powerful this model could be based on different types of data sets. And there's no additional hyperparameter tuning we've done here, or we've not even used the pre-trained embeddings here. So generally, pre-trained embeddings give you some enhancement over what your model does with just learning your own data set. And then once we have that model trained, essentially we just run some predictions on those models. So in this case, we're just sampling some 8 random examples from the test data set, and we can see how that performs on our model. So if you see this, these are the different predictions that we are making, and you see it is predicting correctly based on the test data evaluation. And there are some which are not correctly predicted, and it does tell you what are the different labels being predicted. So this is just a basic sample example, and if you look at this notebook, you would be able to get a better idea of how these models can be built. And then I'm going to focus more on what more enhancements you can do to these type of models, so that you can achieve better accuracy and some basically fine-tuning methods. So the main thing we wanted to see was, in this type of architecture, what we can do is we can choose to learn. So we are going to learn the weights in the fully connected softmax output layer. That just shows you what's the loss of an error. And then we also can learn weights on the convolutional filters. And the one thing which is optional in this type of architecture is learning whether to choose on embeddings or not, which they already explained is you can choose to learn it or not, whether you are using pre-trained embeddings or not. So when I was talking about bucketing, this is something which has been really useful to us in terms of increasing the training speed as well as grouping these different sizes of data together. You can imagine something where a user is typing in our banking chatbot, where the user is giving a feedback which is, let's say, 200 words long. And in another case, if a user is saying pay a bill, that's just 3 words. So if we try to form these batches together, what we do is, with these padding approaches, we essentially try to group these things together. And if you can see, there are so many paddings added to these shorter examples. And then convolutions happening on these padding sequences are not really useful because they are mostly on the bigger padding sequences. So what we can choose to do is follow a bucketing strategy, which is basically forming mini batches of these different sizes of inputs that we have. So if you can see, there are similar sizes of samples that you can look for in this, and then you can convert such type of system with something of the mini batches that we look in this scheme. So you are basically grouping the larger sentences or larger description texts together to form one single mini batch. And in this case, the model is going to consider every single mini batch, and the feed-forward architecture is going to differ for every single mini batch. Although it's different, the learnings that the network is learning based on the weights, it's shared. So anything that these different mini batches learn contribute to the same weight. So that just captures how we can not discard any information from these scenarios, or we can also use the shorter sequences to learn the most. And then talking about pre-trained embeddings is something which is always given an additional benefit to what your model is doing at this moment. So pre-trained embeddings are basically providing more context. They are usually trained on a bigger corpus than yours. Something like word2vec, which is trained on several different corpuses. You can also choose to use the Wikipedia corpus or a common crawl corpus, where whichever belongs or resembles more to your data set can yield you more better results. In this case, we have several different types of pre-trained embeddings which we can use. And Gluon NLP has really good interface with 3 lines of code. You can just load those. But one thing out of these types of different word embeddings, what we can look at is FastX. So FastX is something which was released by Facebook Research. And FastX is basically creating this word embeddings based on, it's just the similar way of finding the context of these words. But the upper edge that FastX has is basically, while creating these mathematical representations, it's creating embeddings or representations for n-grams of the words. So if there is a word which is not available in your trained data set, these out of vocabulary handling of these words can be pretty efficient if you have something called subword functionality. So think of it as if you are trying to say pay a bill and the second utterance is pay a bill with triple L. So that specific bill with triple L might not be existing in your data set. So that can also throw you off from the actual prediction. So in that case, if you are trying to form these subwords, so what it's going to do is, looking at the bill itself with triple L, it's going to break that down into specific characters along with the n-grams of those. So the 2 gram of bill is BI, IL, and then double L. And what it's going to do is, while creating the representation for that, it's going to create a normalized average of these different embeddings that is created. And that just gives you a better support of out of vocabulary tokens, which you would often notice in production deployments. Because there is always a good case where some of the tokens are not present in your training data set, and this gives an efficient way to handling these. So another type of model which was released based on the model we've seen in the past, although this is a model which was a part of entity recognition algorithm, what this is doing is, since we've looked at creating word embeddings for the tokens or word levels, what this can do is it's going to break that specific word into characters and then create a word embedding for each of those characters as well. So in this case, what happens is it will try to leverage the positional context of when these different characters occur together along with the word tokens. So if you were to build such types of models, the feature set would look like the first feature would be the word token itself and the mathematical representation of that token. And then you can have, in case of Picasso, the first feature is Picasso's representation itself. And then you have 7 different letters in this. So you have 7 different representation for each character. So your entire feature set would look like the first word itself and all these characters. So that would be 1 plus 7, and the feature set will now include 8 features. And this again will support more on handling these out of vocabulary tokens and learning different types of punctuations as well. And then you can change your pre-processing pipeline related to these type of models. One more enhancement which you can do is basically looking at linguistic features that Spacy provides. Spacy is basically a NLP library which provides different types of NLP tasks or models which can be used directly. They already have pre-trained version of those for several different languages. So in this case, we have several different features. Some of them are rule-based and some of them are model-based. If you look at shape, so that's basically a rule-based feature which is going to describe what the shape of your word looks like. So if there is pay, it's going to be represented with 3 axes. And there are model-based features which is pause tagging or dependency parsing, which is which provides an additional information of how that word belongs to your dataset. And then what generally in NLP, what you can do is the findings have shown that the words that have similar pause tags or part of speech tags belong really near in the embedding space, or they are usually similar together. So these type of enhancements can bring your model one step ahead. So Spacy provides all these types of different features with just a single function call. So that's pretty handy when you are trying to improve these models after a stage of plateau. This is one more type of model, which was, I think it was an initial approach of using these deep convolutional layers. These deep networks have been really popular in computer vision, but this was a first approach in NLP again by Facebook, where they trained these models, which are again character level models, but they trained it with a huge amount of deep layer stack. In this case, it was including 29 convolutional layers, which is not always seen in the NLP. NLP different the algorithms or models that you see. So this was a first attempt to training these deep models, and it became a state of the art for several different NLP tasks. So this essentially provides one more benefit, is basically the pre-processing of these types of data set can be eliminated if you are trying to work with these models at character levels. So if you are looking at pre-processing for different languages, for English languages, pre-processing would look different. For Chinese, let's say the chunking models, or there's no real character, or the breaking down of those tokens is quite different than what you do in English. But with this types of models, you can essentially feed the characters. It doesn't matter what that character represents, as long as the model is able to learn this character and the representation of those characters. These deep networks usually learn good amount of learnings from these contexts of occurrences of these different types of data sets and mappings to those categories. So looking at these different types of models, then one more thing which I forgot to mention is in the previous year we have seen pretty good advancements in NLP based on transfer learning approaches. One of the initial was the ULM-FIT, which is the Universal Language Modeling and fine-tuning purposes. So in that case, what you essentially do is, instead of pre-trained embeddings, which is now considered a pretty basic way of identifying larger data contexts, with this ULM-FIT, they introduce something called learning from language models itself. So these models are learned, language models are learned based on, let's say, really big data sets. And then those learnings from those language models can be used in the specific classification task. So in this scenario, the classification task can only take really few examples to learn. And it was based on as few as 100 examples, the model reached the state of the art. So in that case, those are the pretty new advancements in NLP, which has been helping to probably move ahead in these NLP classification tasks. when we are looking at these types of models, one of the problem or the feature that we look at after these models are producing predictions is basically the confidence or the thresholds. So every prediction is made, it has some probability assigned to it, which is telling you how confident that model is about that specific prediction. So what we do is basically we visualize this in different types of predictions, and we identify what are the incorrect predictions along with the correct predictions. The ones that you see in the yellow bars are the correct predictions, and we define these thresholds, which is basically telling you should we consider this prediction or not. If we define these thresholds, any predictions made under, let's say, 0.50 is not going to be considered as a prediction, and then there's a business logic associated with this. So we often try to move these confidence thresholds based on the precision that we are trying to achieve, or the accuracy of these, or trying to reduce the false positives predicted by a model. So when we talk about these thresholds and evaluation criteria, there are specifically two different types of evaluation criteria that we take in, which is precision and recall. For those of you who are not aware, precision is something, it's just a number which tells you out of all the model predictions that the model has made, how many of those are correct. And recall is something which tells you out of all the annotations that you have done, how many of those are correct based on the model predictions. So it just gives you a better way of looking at specific categories. So you can see on the x-axis, it represents different categories of these classes, which we can call as intents. So the intents can have, the examples that we saw, it had 4 different classes or categories, but intents in this scenarios can range from, let's say, 50 different intents to 100 different intents. So we try to look at these different intents specifically and how each of those predictions are performing on specific intent level. And then one more additional evaluation metric is the F1 score, which is basically a harmonic mean of precision recall, which is a good evaluation metric based on intent classification model, also on the tagging models that you find, which is named entity verification model. Once you have evaluated these type of models, you have a problem. So basically recall is, when you look at precision is something where out of all the predictions that model makes, how many of those are correct, how many percentage of those predictions are correct. And recall is something where out of all the annotations that you have in your data set, how many of those are correct. So predictions, precision is based on just how many predictions are passing through the model, and recall can be evaluated based on how many true values you have entirely in your data set. So that means those values in your data set might not be predicted because it was never passed to the model. But in that scenario, it provides a better view of how that is performing based on the data set capacity or the labelings you've done. It evaluates basically the quality of your labeling. So model calibration is something like when you are building these machine learning models, as and when these models get more complex, the one on the left you would see is the ideal machine learning one, and it just shows you how confident this model is. So in an ideal machine learning model, the calibration looks something like whenever a model is very confident about the prediction, it is always the most accurate. But when you make these machine learning models really complex, if you look at several deep learning models and stacking new layers, that becomes a complex model. These models generally produce a not well calibrated graph, something you see on the right, which basically tells you whenever a model is confident, really confident, it's not very accurate. So that just shows you the differences between being very confident and being very accurate. So the model could be very confident, but in true sense, it's not very accurate. So these deep models suffer from these calibration problems, and that's something which is actively worked on. And you would face these type of problems when you're experimenting with several different complex models. And the last problem that I'd like to show is one of the most challenging problems that we are facing is called the intent boundaries. So what we are doing is basically we look at our model and we are taking the softmax layer output of our model. Whenever any utterance or any text is fed in the model, we are looking at what the softmax output produces, and we are taking that output and providing two-dimensional plotting for that. So this shows us where or what does the model think of any different types of text that is fed into that. And in this scenario, we're able to visualize what different types of categories of the utterance belong in the dimensional space. And if you see, there are two different classes here, or intents, which is a goodbye intent and a thank you intent. And imagine if someone says goodbye, that can be predicted to goodbye. But if someone says thank you, it can also be predicted thank you. But someone is trying to stop the conversation. If someone says, okay, thank you, goodbye, it comes together, that becomes a problem of ambiguity where it can also belong to one of these classes. So that's where we try to find out where are the different cases where these type of intent boundary problems happen. And this just provides a better view of how we should try to annotate these different utterances to specific classes, and how we can strategize these defined classes in a better way. So to end on this note is basically explain how that NLU or intent classification these type of models can be built using MXNet. What are some different challenges that you could see, and what are some enhancements you could make to those type of models. But if you look at the bigger picture, when you look at these conversational AI systems or the dialogue systems in general, NLU is basically just a smaller part of the bigger system. That's where NLU, natural language understanding, sits. And intent recognition itself is again a smaller portion of natural language understanding. So natural language understanding usually generates intents and entities, or you can call them thoughts. So those two are the different models that I explained in the first slide, which is basically part of NLU. But when the bigger system is considered, the dialogue system is not just limited to understanding the utterances, but to also first understand the utterances and producing intents and entities for that. And then you have some state tracking mechanism which will track what are the informations or what are the different information that have been extracted from the user input, and then what you do with those set of information. So there are basically two different components in that. So when you're looking at a dialogue manager, it has two main components. First of them is a state tracker, which tracks what is the information that has been received until now and has been found from this specific text or utterance. And the second is dialogue policy learning, which basically learns what is the predicted actions based on what input I've received. So it basically receives the input from NLU, dialogue manager, state tracker will track the information received, and then policy learning will try to map what are the actions should I take based on the information I've received until now. And that basically gives a dialogue manager a way to handle context in different conversations. So if you are, let's say, paying a bill, you would just first specify pay a bill to my friend. So in that case, the intent identified as a payable intent, so that state tracker would identify payable intent, and then it knows that I'm missing some information based on how much do we want to pay. So then it's going to predict the action based on since these are the informations you provided, I'm missing amount that you want to pay. So the next action that is given out of the dialogue manager would be request amount. So that's what this dialogue manager will do, and then it will pass it again through some type of response type. In this case, it is natural language generation. We can still omit this part and try to find some different ways of serving this response system. So once you have this request amount, you will serve that response to the user. Once the user has that, user will respond back with, I want to pay $100. And in that case, again, you will go again to end and it will try to predict what the user is intending to do. It will try to extract entities which is $100 as amount, and then it will again feed that to dialog manager, which again tells you, I've received the amount. Okay, so let's confirm. So that's the next action this dialog manager would try to predict. So this is how an overview of dialog systems look like. So anytime you see any of the conversational systems that you often see, it's basically operating in this principle, and it has natural language understanding, which understands what the user is trying to say, and then you have these dialog managers which try to track these informations that have been received, and then predicts based on that what to give the response back, or what should we ask the user back. And are we missing any information from the user? If yes, we just prompt the user that provide me these information. That's how we complete these conversations. So that just gives an overview of how dialogue systems work. And then these are the systems which were rules-based earlier, but now you often see the advancements on neural dialogue systems, which actually takes all of these components and they try to make them all end-to-end differentiable. So they all can be represented by some form of neural networks, which again jointly tries to learn what the user is feeding in and what the output goes out. And generally, it has been found that these neural dialogue systems work really well because they try to capture something which not always can be learned from these tools. So it is still an active area of research, but it is advancing really fast. So you would really find these type of systems where deep learning is leveraged to build these deep learning or dialogue systems in the future. So I think on that note, I just end the presentation here, and feel free to ask any questions. Yep.
So you showed a little screenshot on one of your first slides about your system being used, and a lot of what was there was actually not natural language, but interaction deeper in the dialogue. Do you have statistics of how much of that is used versus true natural language dialogue steps?
Can you tell me the slide are you referring to?
It was one of the first slides you guys had where you had like a sample conversation. I don't know, maybe it was, oh yeah, this on the right side. So you can see that basically a lot of the conversation of the dialogue here is driven by interactive buttons, right? Which is more a UI system than a natural language system. So is this a consequence of you guys not being too deep into that whole dialogue policy learning, or is that just something that is a side effect of how these UI want to be designed by customers?
So the demonstration that you see here, it is basically showing these buttons, but those buttons can actually work if you submit the text input as well. And the interaction with the bot or this system is not limited to what you can see in the buttons. So as I said, we have hundreds of different intents. So there are different responses that we can support, and all those intents are basically trying to learn what user is trying to say. In this specific scenario, you can, if you're just thinking about how these buttons are operating, it's really limited. But it's when the explanation that I gave about the text classification models, that's where these natural language understanding comes in, where we have 100 different types of intents that we can predict to. And it's about understanding these different types of use cases. If you say pay a bill, you don't see pay a bill to my friend on the buttons. There are like several different examples that you can take. Where's the nearest ADM to it? It's not available directly in the buttons. So that's where the NLU comes in.
But I was just wondering how the distribution is between users using the interactive means versus like actually typing that in. Because the other thing is, you're just faster, right? And on a mobile device, as you show here, typing a button compare is easier than compare the first two. Right? I have to type this, I have to use two fingers maybe, and so on. So do you have a data around how many customers or how many dialogues kind of use natural language in deeper dialogue steps or versus kind of actual natural language?
In terms of usage, we find about 4 or 5 times more interactions via UI dialogues. You're correct in saying in some cases it's easier to use those buttons, but in many cases those buttons don't exist, and it's easier to use conversation. So for example, if you want to say, pay $50 for my checking account to pay my BC hydro bill, it'll just say confirm, and then you press confirm. You can't do that interaction using just buttons. You can, but it takes several steps, it will be a lot more difficult.
Okay.
Thank you for the presentation, Ron. Appreciate it. My question is about the architecture you chose. Is convolutional the better suited architecture for this type of use case compared to some of the sequence models like STM, GRA, or even attention models?
Yeah, so yeah, it's actually a surprising thing that on these type of sequence models, usually LSTMs or earlier RNNs were used and then LSTMs came in. But the good thing about convolutional neural networks is they work exceptionally well in terms of identifying the context. So when you're passing these filters, those filters in those convolutions actually try to cover the context of the reference itself. So in this case, if you're saying pay a bill to my friend, the filter actually goes through the surrounding words, and studies have shown that CNNs work exactly almost at the same level at RNNs in some of the cases. So even in the entity recognition models, RNNs would be a better suited candidate, but again, when you have CNNs introduced there, they outperform in some tasks, or otherwise they always try to match up the performance of these RNNs or LSTMs that are provided. And again, one more addition to that is when you're trying to use something like attention mechanisms, they can also yield a better systems or better outcomes from your model. But CNNs generally capture those contexts within the utterances based on the filters we are using in the conversational network. So it has found that it's really almost at the same level when you are looking at these NLP tasks. Although CNNs were traditionally looked at, they belong to computer vision or looking at the images, but it works surprisingly well on NLP.